Hi everyone, and welcome to our video on the polar form of complex numbers. So we've got our complex number form, the z equals a plus bi. It also has a polar form like that. Let's show where it comes from. Okay, so just to the side real quick. So if I had a plus bi, so say a is something like that, I don't know. So we don't need the tick marks. Let's get rid of those actually. So let's pretend it's just like to the right and then up. Okay, so let's say here is where z is. Well, I can again get my right triangle involved. And let's label those horizontals and verticals. This would be a length of A, that would be a length of B. In standard position, I know that my angle right there is theta. Let me try it one more time. There's my angle theta. We said that the length from the origin to the point is the modulus. So that length right there would be the absolute value of z. But we just kind of in the previous video said, well, it's usually we talk about r with radii. So often we just go ahead and say, well, let's just change this to be r to kind of match our polar form anyway. And then from there, we can use SOHCAHTOA. So SOHCAHTOA. So the sine portion, we would have sine of theta equals our opposite b over the hypotenuse z, the modulus. Actually, let's change it to, so I said just z, but let's just do r. And then the cosine portion, that's all I'm going to focus on, just these two, would be the adjacent side, which is a in this case, over the hypotenuse r. Let's solve for the a in this cosine equation. So multiply the r over. So a is equal to r cosine of theta. Solving for b in the sine gives us b equals r sine of theta. And so let's go back to our z equation. So z is equal to a plus bi. And so let's change the a and the b into what we have above. So we have z is equal to r cosine theta plus b, which is r sine of theta. And then the I would be attached afterwards. And then we could see, well, the r can be factored out. Let's also just move the I. So r gets factored out. So we have cosine of theta plus, and then to avoid confusion, we'll just put the I right there in front of the sine. I sine of theta. So that's where it comes from. So SOHCAHTOA again. So SOHCAHTOA usually is what we need for majority of things in this class, along with the unit circle. All right, so anyway, let's break this down and start to solve this. So write the complex number in polar form. So I would still sketch it. Okay, so 6 to the right, and then down 6. There it is. And then we need to convert it into polar form. Okay, so what we want is that length in the blue, and then we would want that angle. Okay, so notice again that this is our A and B in this problem, or A is 6 and B is, and our B, so actually let's label those. So our A is 6 in this problem, our B is -6, just to match those. And really, so I just broke down the SOHCAHTOA portion, but the other thing that's important with right triangles is our Pythagorean identity. Okay, so we could just say, well, a squared plus b squared is going to be that r squared from that picture. Or again, remember, r is the modulus of z. And I didn't break apart the tangent one, but the tangent of theta would have been the b over a. Okay, so the opposite over adjacent. Okay, so those can also help us in these scenarios. Okay, so in this problem, we still have a right triangle, and we could still always draw those in. So there it is. There's the 6 and 6. And then I can use Pythagorean's theorem. We would have 6 squared plus 6 squared is r squared. We would get 36 plus 36 is r squared. 72 is r squared. And then when we square root both sides, okay, I'll just keep it in blue. This would simplify to be r is equal to 6 radical 2. Okay, and you might have caught that earlier. So the square root of 72 does simplify to that. Or you might say, oh, that's a special right triangle up there that with the same sides as 6. So that means you could just multiply by radical 2 to get that radius or the modulus of z. Okay, so we know that part. Okay, and so what we're going to do is just we're setting it up. Let's go ahead and write this here. So we just need to do our conversion. So we now have r, 6 radical 2. Notice I usually put plus and minus. Let's go ahead and do that again for habit. Oops, just on the number part. But we would want the positive value in this case because we're kind of looking at it using our circle vocabulary. Let's keep it positive. Okay, so far I've got that. And then what I need to find is the theta there. So cosine of, well, again, if you see that it's a special right triangle, we can maybe figure it out right away without too much effort. However, if we don't see it right away, that's where I would use the tangent of theta. So tangent of theta would be our opposite, so b over a. But our b is -6 in this problem. Our a is 6. So we do have tangent of theta is -1. And then that's solved for by using the unit circle. It's either in the fourth quadrant or the first quadrant, or second quadrant, I mean, fourth quadrant or second quadrant. And based on our picture, we would want the fourth quadrant one. We're going to do 7 pi quarters. Okay, so you can have different answers as well. However, typically we keep them in our 0 to 2 pi range. Okay, so that means our cosine has 7 pi quarters with it, and then plus I sine of also 7 pi quarters. Okay, so that's converting it into the polar form. Okay, so complex number converted to polar form always looks like that. So our focus is to find the r. I didn't label the r. That's r. Is to find the r and to find the theta. Okay, so for number 2, okay, so I might have squeezed too much room out of there. Okay, either way, again, I'm going to quickly sketch it. Let's put the sketch right here. All right, so I've got negative radical 2 and then plus radical 6. So radical 2 to the left and then up 6 is probably somewhere about there. And let me color code. Okay, and just like before, we can still label our triangle. Okay, so there's the radical 2 and there's the radical 6. Again, geometrically, I usually keep them positive. Okay, and then in the blue is the r. And then in the purple would be the theta. Okay, so there's everything marked up. All right, and so what we need, again, I want my equation. Let's go ahead and set my equation up down here. I want r and then cosine of theta plus I sine of theta. So I just need to fill those in. Okay, so to get r, I can still just use Pythagorean's theorem. So we've got r squared is going to be the radical 2 squared plus the radical 6 squared. So I'm just looking at my triangle right there and plugging in the legs and squaring them. Okay, and then when we do, we get r is equal to radical 2 squared is 2 plus radical 6 squared is 6. So r squared is 2 plus 6, which means r squared is 8. And then we can finish this one off. If we square root both sides, we're going to get r is 2 radical 2. Again, I can put the plus minus, but we would want the positive r in this problem. Okay, so that part's ready. Now I need the angle. Okay, so let's do that in purple. So I've got the tangent of theta is equal to our opposite over adjacent, or our a over b, or a b over a, I mean, sorry. So our a is negative radical 2. Our b is positive radical 6. So we would have positive radical 6 over negative radical 2. Now, the radicals would simplify with each other. This does become negative radical 3. So 6 divided by 2 is 3. And then we can use our unit circle to help us. It's again negative, so we're either in quadrant 2 or quadrant 4. And I could even draw that, let me draw it a little better and bigger. So all that scratch work to the side is kind of in the way, but let's put it like that to make it a little bit more accurate. So where tangent has a radical 3 involved is closer to the y-axis. Okay, so, and I want the one that's in quadrant 2, so it would be 2 pi thirds. So using our unit circle, we would get that angle. And then now I can plug all of that information in. So we've got r is 2 radical 2, parentheses, cosine of 2 pi thirds, plus I sine of 2 pi thirds. There we go. Okay, so that's how we can convert a complex number into polar form. Okay, so I'll draw on a sketch. Again, I kind of notice it's very similar to our polar coordinates, rectangular to polar as well. So it's kind of a direct connection. Okay, anyway, that's it for now. Let's take a pause and we'll deal with the next stuff in the next video. Thanks for watching.